Hello and welcome. I'm Nicolai.
And I'm Mathias.
Yes, and we will present to you this roller coaster ride we have been on with our master thesis called Automation of Robustness Analyses, where we used Revit, Dynamo and Python. We have a background within building structures and have a special interest in BIM and how it can be used to help in these analysis of the structures. This is our agenda for today. We'll talk about the background for master thesis. Then we will go through this product we have developed in our thesis. And last but not least, we will talk about the results and limitations and potential of this product. First of all, our motivation for this topic is quite clear, as we want to help in regards of preventing these large, major and progressive collapse that's been seen around the world. But as we don't have any experience ourselves with the collapse, we have a personal motivation from a course we have taken here on BTU called 1108, where one of us was the designer of the structure, and the other one had to be aware of the fire calculations and the fire structural. Yes, exactly. And yes, this course we designed a high-rise building, as you can see here. And as we talked with our teachers in this course, they asked us to find the most critical and most important elements in this structure. But since we didn't know how to do it, we asked how do we find these elements. They said use your logic and use your experience. And since we didn't have much experience with finding these key elements, we put up some criteria to find these key elements. In this case, we looked at the loads and load combinations. We looked at the risk of loss of human lives, and we looked at how many other elements were dependent on this element we were looking at. And by that, we found these key elements that we thought would be important for this structure. Later, we also talked with Anders from the engineering company Revit, where we got some input about how it's been done in the industry, and we would talk about one method about static analysis of a 2D structure, where you look at the loads and find if you remove a part of this 2D structure, if it has an overturning moment, which will cause the structure to collapse and not be stable.
Yes, so these experiences from the course 1180 and this manual method, which takes some manual hours to do, we thought of this problem statement for our thesis, which is about assessing or studying whether it's possible to develop a workflow or a tool to help us in assessing this structural robustness in any kind of 3D model. So in order to do this, we dived into the European and Danish standards and to see if there was anything we needed to be aware of. And we quickly saw that they differentiated between the principles, which is like criteria you need to address, and some application rules, which are recommended workflows or methods to ensure these requirements. And an example of a requirement is that all structures need to be designed to prevent progressive collapses. And a way to do this could, for example, be to design these key elements so that the localized failures in a structure that may occur will stay local. The Eurocodes also present this figure here, where they base their strategies or their methods into different strategies. The first, or the left ones, are based upon pre-identified collapse collapses or actions in the building, whereas the strategies on the right side are more like general observations. So yes, our primary focus are these key elements which we want to locate. Here it says that they can be designed. In order to design them, however, we want to locate them first, and that's what we thought about making a method to do. Our initial concept, or actually the whole idea of our tool, is to, if we have any arbitrary construction or a 3D model of a structure, we should be able to somehow, if we could be able to simulate all these different kind of accidental scenarios, we could, by the use of some kind of software, maybe be able to somehow assess which of these scenarios are the most critical ones for the structure. And in this way, kind of estimate where you need to have some extra focus when you design a structure. To do this, we use some different kind of software. The primary software is Revit, Dynamo and Python, which we had some previous experience with. However, we also saw that in order to create such kind of workflow, we also needed to gain some quick knowledge in coding in Python and some knowledge of these two file formats, which is called XML and CSV file formats. Since we only learned the Python coding, or actually to do this to create this tool, we're kind of new to it, and that's also why that some of the codes might be optimizable, or actually it may also be rewritten so that it's more easier readable if for example follows some kind of standard like the Type 8 standard, if you know about that.
And from all this software we just talked about, we created this program, this workflow we call the Iron, and it consists of 5 steps. The first step is painted green in order to show that the user has to prepare the model. They have to do some manual work. All the red boxes symbolize that the process is automated and can be done by a click with the mouse. And we will go through these steps now.
So the first step we actually call step 0, and that's in order to illustrate that this step is actually done manually prior to using the automated method that we created. These properties are something that needs to be present or be defined in any of the models that wants to be analyzed, and this is actually general requirements for any structure to be analyzed in some kind of software. And this includes defining some cross-sectional data or material properties, some connections, the loads and the load combinations they correspond to, and the boundary conditions. And you also have to be aware that the structure is properly connected, and it's not just seemingly properly connected. There are some, you have to be aware that these analytical models need to be properly connected. In addition to all these more like general properties you need to define, we also set an extra requirement in order to be able to simulate all these different failure scenarios. Usually when you create a building or model it, you model it with the whole wall sections as being one. But since we want to be able to take a small part out of the wall in order to simulate all these scenarios, we divided or created an algorithm that divides all these wall sections into, or wall elements into sections of 0.5 meter. It's not always when you model such a wall that the length is exactly divisible by 500 millimeters. And that's why the algorithm takes the leftover length and divides it out onto puts it out onto all of the other small sections. So in this way, you get all of these elements, which are 500 millimeters or a little bit more than that. You can see here that the algorithm, you can run it by this use of Dynamo, and it takes all of the wall elements and creates these smaller sections. Yeah.
And now that we have prepared this analytical correct model, we transfer to a FEM analysis program, in this case FEM-Design, where we have this original analytical model we call the model file. And this model file we copy as many times as we have failure scenarios for the building. And if you, for example, have a building with 1,000 beams and columns, you will have 1,000 different failure scenarios, and therefore also 1,000 different kind of models you need to have.
Yes. So with all these copies made, right now they're actually just identical copies, or they're identical with the model file. So they're all the same. What we do now is we use our knowledge of modifying these XML files, and in this way, by opening the XML file, removing an element in the XML file, it actually corresponds to removing an element in the actual model. So in this way, we actually just removed a model or an element in the model. We have just one back. We have these different scenarios defined, which is 6 wall sections, which corresponds to 3 meters of wall, a single column or a single beam, and these are the base for all of our different scenarios. Since the algorithm we created is happening, or it does its work inside of the computer, it's not really visual. It's not that easy to see what happens. So we created this video here, which illustrates that you go into an XML file, one of the copies, remove an element, close it again, and go into the next file to create a different failure scenario. So in this way, we create, in the case of 1,000 copies, 1,000 different and unique failure scenarios for a model.
And afterwards, when we have all these different unique analytical models, which corresponds to a failure scenario, we analyze it with the help of FEM-Design. And in this case, you can see we have removed the corner of the first floor in this building, and the analysis is run. And this is done for every single file by the field allows for all these, for example, 1,000 different failure scenarios. Afterwards, we get out a result file. In this case, it's a CSV format, which is a text file, which contains all the utility ratios that's been calculated in FEM-Design for every element in every analysis. And by finding the maximum utility ratio for each element in each analysis, we can make a big CSV file containing all the maximum utility ratios found for each analysis. And in this case, we get a very large data file.
This is the maximum utility ratios for every single element in every single failure scenario. So it's quite a lot of numbers. Now we have created this summarized CSV file, and we need to somehow take the data and do something with it. We've chosen to visualize the results from our analysis, and we have chosen to do this by defining 4 different categories, from which the most critical ones, the elements that are colored red, are the most critical ones, whereas the elements that are colored transparent, I don't know if that's colored, are the least critical ones. We developed these 2 different kind of methods to do this. The first method is based upon a set parameter, which we can say is a lower value. In order for the elements to be given a color, these failure scenarios needs to overcome these lower values in order to be colored accordingly. This, however, means that if no elements in any of the failure scenarios fails, which means that you have no critical elements, this first method actually doesn't color any of the elements at all. And that means that the user might need to define some proper parameters instead of the ones used. Instead of doing this, we actually chose to make a more generic method, which instead of using these lower values, actually defines an upper value from the most critical failure scenario. And from this, it defines the other categories. This results in us ensuring that at least one of the elements in the building, at least, becomes red, so that the user gets some kind of thing to think about. This visualization for this building, for example, can be seen here. And from the method, it can be seen that the area around the opening of the building, these elements down there are actually the most critical to remove. And it means that if an element is removed down there, it causes the most other elements to fail if it's removed.
Yeah. And in this case, the beams and the columns is not painted. This was due to this video made earlier in the process, because I had to present it before. And it was just to illustrate that we had also included not just the wall, but also included walls and beams.
So this was prior to adding the walls, the columns and the beams. Yeah.
Yes. A quick summary of our workflow. First, we have these 5 steps. First of all, we have to make an analytical correct model, and in this step we also divided the walls into smaller wall sections to get a more thorough investigation of the model. Afterwards, we copied this analytical model into as many failure scenarios as there are for the building. These failure scenarios was created in the next step, so that we had a unique model for each failure scenarios that can occur for this building. Afterwards, we analyzed each failure scenario in web design, and by that we got some output which we could use to colorize our structure in order to give the user an overview of the most critical areas of the building.
So the results of our process of using this R method is that we can locate the critical key elements. As the program is right now, that's not enough as a standalone to assess the full structural robustness of a structure. We need to design these elements which we found. We need to take some supports and connections into account, and some details regarding if you have any tensile ties that holds the building together. You can also improve some of these assessments by checking if there will be any elements which causes directly progressive collapses, and you might also take the risks into account.
Yes. And when we tested this workflow on these different kind of models, we also saw some limitations for workflow. First of all, we saw that the workflow worked better for 3D models than 2D models due to the workflow taking into account the maximum amount of overutilized elements when you remove one element, and due to 2D models missing the third dimension compared to the 3D models, we got a better result in the 3D models. The process time is also different according to the size of the model. Here, the first one, we see a model where the process time for modifying all these XML files, all these analytical models, is nearly constant for every single file, whereas when the model gets larger, the process time is no longer totally constant. Sometimes it goes up to as much as 7 hours for one file to be modified. And this was due to the computer's RAM being totally used, and we therefore had to stop the process and remove the RAM and then start again. We also looked at the process time of the entire workflow for these models we tested, and for this we found a nearly exponential growth in the time when the model size, the element size increases. And by this we found that 400 elements in a model would take roughly a day to analyze with this this workflow. 1,100 elements would take roughly a week, and 1,800 elements would take roughly a month. Regarding that, the computer has enough RAM to do the process.
So in the end, we defined this problem statement where we wanted to study whether it was possible to create some kind of method or tool to help us assess the structural robustness of 3D models. We then developed this workflow, which you just saw, and we know that, or we at least really believe that it's possible to optimize these algorithms. It's probably possible to not get these RAM problems, or at least minimize them, if you somehow divide the steps into several sub-steps. You might even use some other computational software or analytical software to get some completely different results. This workflow, which we created, it might even, right now, when we think about the potential, with the use of FEM-Design, we're not actually using the whole potential of the use of this software. We chose to only use the maximum found utility ratios of the different elements, which says that they will collapse or fail. But actually, when every single result or analysis is made, we actually get several utility ratios of each element. So we might actually be able to improve this workflow as it is by, for example, not only locating which elements will fail, but also how will they fail. So this might be some extra work we could do in the future. But when we talk about potential, we actually think that the potential is not only limited to robustness analysis. We believe that we have some previous experience with some what they call parametric design tools like Dynamo and Grasshopper, and we know that you can, in a very, very short time, create hundreds or even thousands of different kind of design proposals for example, a structure. And then now we also have a method of actually calculating each of these different solutions to, in the end, maybe help optimize or, in the end, design some effective structures. And that was actually the end. And we would love to hear your comments, or if you have any questions, or if we need to elaborate anything.